Hey everyone, this is Mrs. Villette, and I'm going to recap function transformations. We'll go over horizontal and vertical shifts, which you should be very familiar with, and what might be a little bit new or unfamiliar to you is the vertical stretch, compression, reflection, as well as horizontal stretch, compression, and reflection. So we're going to suppose that you have a function f of x that only contains the point 2, 5. Which point would exist on the following transformations? So first, let's interpret this point 2, 5 in function notation. We need to think of this as meaning f of 2 equals 5. We'll go ahead and plot this point 2, 5 here. So this is 2, 5, and it's on f of x. Our first example is a of x equals f of x plus 3. Well, since there's no change on the inside of the function, and my function only allows x to be 2, that means the only reasonable thing for me to do is to plug in 2 to a. So a of 2 would be f of 2 plus 3. Well, what is f of 2? F of 2 is 5. So 5 plus 3, which is 8. So the ordered pair we'll have is 2, 8. So 2, 8 is over here on f of x plus 3. This corresponded to a vertical shift by 3 units. Now we have b of x is f of x minus 4. Again, there's no change in the x value, so the only x value I can plug in is 2. b of 2 is f of 2, subtract 4. But what is f of 2? It's 5, and 5 subtract 4 is 1. So I have the ordered pair 2, 1. So here is the ordered pair 2, 1, and it's on f of x subtract 4, which is a shift down by 4 units. Okay, now we have c of x is 3 times f of x. Again, no change to the x value. So the only x value I can plug in is 2, because that's the only value this function has. So I have 3 times f of 2, or 3 times 5, which is 15. So I'll have the ordered pair 2, 15. I don't actually have enough room to do that. So right here, 2, 15. Now I don't want to think of that as a shift up, I want to think of that as a vertical stretch. So if I go from 2, 5 to 2, 15, okay, sorry, there's going to be an awkward transition here. I had to change audio sources, and it's not going to sound as good, but previously it was picking up the air conditioning, which sounded terrible. So what we want to look at is our original point was 2, 5. What happened was the y value ended up being multiplied by 3. So it's a little bit hard to tell when it's a single point, but if you actually look at how that number 3 showed up in my transformation, here it is, multiplying by 3. So similarly, on d of x equals 1/2 f of x, no change to the x, so I'm going to put in x equals 2, but the y value will now be half as large as it was previously. So if I put in d of 2, I would end up taking half of f of 2, but f of 2 is 5. So that's all of the vertical transformations. We've got shifts up and down, and we've got stretches and compressions. We also have vertical reflections, which we'll see an example of later in the video. When you get to the horizontal stuff, first of all, horizontal transformations happen inside the function notation, and they happen reverse of what you would think. So let's start with this example, and let's pretend we didn't know that, and we just blindly try to do this problem. So e of 2 is f of x plus 3. Well, you might do what we were doing in the previous problem and plug in 2. Well, that would be f of 2 plus 3, which would be f of 5. But we said my function only allows 2 to be the input, so that doesn't work. So we try again. I have to think, what x value would I need to plug in here so that my result is f of 2, because I know what f of 2 is. Well, I'd have to put in a number that's 3 less than 2, so negative 1. If I do f of negative 1 plus 3, and then I follow order of operations, negative 1 plus 3 is 2, and then f of 2 is 5. So I have the ordered pair 1, 5, negative 1, 5. That corresponds to a shift left 3 units. Notice the function said f of the quantity x plus 3, but we weren't actually adding 3 to the x value we had previously. We were figuring out what do I need to add 3 to get the x value I previously had. So it's more like we're solving on these horizontal transformations rather than evaluating. So I think, what do I have to put in to work out to be what my original value was? Our next one, capital F of x equals f of the quantity x minus 4. So I'm thinking to myself, what x value do I put here so that when I subtract 4, I get 2? So we could do a little scratch work off to the side or solve in your head. X minus 4 has to equal 2. That means x has to equal 2 plus 4. My x has to equal 6. So I can do capital F of 6 equals f of 6 minus 4. 6 subtract 4 is 2, and then f of 2 is 5. So the ordered pair is 6, 5. So 6, 5, I'm kind of running out of room here, is right there, and that is a shift 4 units to the right relative to the original point. I want you to apply that same idea of balancing out the x values. So in g of x here, I cannot put in 2 because that would give me f of 6, and I don't know what f of 6 is. So what could I put in? I need to put in an x value that is 1/3 as big as my original x value. So I can put 2/3 in. That gives me f of 3 times 2/3. The 3's cancel. It gives me f of 2. I know f of 2 is 5. So we're taking this original point 2, 5, and it became 2/3 5. Notice the y value stayed the same, but the x value was not multiplied by 3, it was actually divided by 3, or multiplied by 1/3. Let's go back to our previous two examples and do the same thing. So we had 2, 5 translated to negative 1, 5, so we were actually subtracting 3 from the x values. And then here we had 2, 5 going to 6, 5, and since this was a shift, we're thinking about adding or subtracting, we added 4 to the x values. So this last one, f of 1/2 x, is actually a stretch, and I think about what can I put into my function so that I end up with a resulting argument of 2. Well, I can put in 4. H of 4 means taking f of 1/2 of 4. Half of 4 is 2, and then f of 2 is 5. So the ordered pair that I get is 4, 5. It was previously 2, 5, and since this was a stretch, not a shift, what did I do? I multiplied the x values by 2. Let's go ahead and perform some transformations on a continuous function rather than just a single point. So in example 2, we're going to have our graph of f of x, which is pictured below. And notice I've zoomed in on the original function, but I've given you more space when we do the transformations. So on the first one, we are doing 2 times f of the quantity x minus 1, subtract 3. How you do these really depends on whether you are a numeric person or a graphical person. I tend to be a graphical person, I'll show you that way first, and then I'll show you how you could do it if you're a numerical person. The first thing I'm going to do is identify the transformations. So on the inside, f of x minus 1 is a shift right 1u. Things on the outside are as they appear and need to follow order of operations. So first we're going to multiply, so this is going to be a vertical stretch by a factor of 2. So we're going to double the y values. So this is a vertical stretch by a factor of 2, followed by a shift down. Now in terms of order, horizontal and vertical are independent of each other. They don't affect each other. So you might start with the shift right, and I'll maybe label my horizontal transformations A, B, C, and then you could do the vertical stuff. So let's label them 1 and 2. Now you can do horizontal first or vertical first, but within the vertical you need to follow this order, the stretch and then the shift. So what I might do in a function like this is take the key points, there are 3 of them on this function, and just apply the transformations all kind of in one step. So this is at -2, 1. I'm going to stretch it vertically by a factor of 2. I'm actually going to move my label down below. So -2, 1. So stretch it vertically by a factor of 2. That only changes the y value. So double the y value. That would take you up here. Then shift down 3. So now I'm going to count 1, 2, 3, and then shift right 1. So here's my new ordered pair, -1, -1. Now I'm moving over to this point at 4, 1, and I'm going to stretch vertically by a factor of 2, which just means multiply the y value by 2. So it's now 2. Shift down 3, so count 1, 2, 3, and then shift right 1. Okay, so far my horizontal piece has stayed horizontal, and that should always be the case. But where we're really going to see something happen is at this piece up here, which is at 6, 8. So I'm going to double 8, which takes me to 16. I can't actually put that on my graph, but then I'm going to shift down 3. So 16 subtract 3 is 13. And I can fit that, so that would be right here, and then shift right 1. So here are my 3 new points. It is still this same shape, but notice the slope of the non-constant piece is now double what it was before. And if you look at my range, the range isn't exactly doubled, but the length of the range is. So my original range went from 1 to 8, which was a length of 7. My new range goes from -1 to 13, which is a length of 14. So you can see that that length of the range doubled from 7 to 14. You can easily see the shift right 1. The shift down 3 is a little bit trickier to see because there was actually a stretch before there was a shift, so you can't really see that shift down 3 effectively on this graph unless you follow the points through in order. Okay, we have another function that has multiple transformations, so I have a -f of 2x. One is on the outside, one is on the inside, so I don't need to worry about order. So I'm going to look at on the inside, this f of 2x is a horizontal compression by a factor of 1/2. The negative on the outside is a vertical reflection so this is going to flip this function over the x-axis. So let's start with the horizontal compression part, or we can start with the vertical reflection. It doesn't really matter because they're independent. So again, we'll take these key points. Let's start here at the point 6, 8. to compress that horizontally by a factor of a half, I am going to take the x value and multiply it by a half, which takes it here to 3. And then, so we went to 3/8. That was my compression. Then I'm going to reflect over the y-axis, which basically just means multiply the y value by -1. So I go down here to 3, -8. Okay, 4/1, compress horizontally by a factor of a half, and then reflect. So 4, not 4, 2, -1. Okay, -2/1, compress horizontally by a half, and then reflect. I become -1, -1. And then it's the same kind of shape, but notice the length of the range did not change. The range previously went from 1 to 8, which is a length of 7. It now goes from -1 to -8, still a length of 7. That didn't change, but the length of the domain changed. So the original domain went -2 to +6. That's a length of 8. The new length of the domain goes from -1 to +3, which is a length of 4. It is half as big. Now a way that you could check this is plug in an original ordered, or not an original, plug in one of your new ordered pairs into your function. So let's say I want to look at this point and see if it's correct. I could say h of 3 is the opposite of f of 2 times 3. So opposite of f of 6. What does f of 6 mean? It means go to the original function, find 6, tell me what y is. It's 8. So this is saying the opposite of 8. That's giving me the ordered pair 3, -8, which matches what I have on my graph. So if seeing the graphical representation is fine with you, you can go ahead and fast forward through this next part, but I'm going to go back and show you how to do it numerically. So to do this process numerically, you still have to understand what each of these numbers does to the graph and in what order. The difference is you're not going to look at a graph, you're going to look at a table of values or some numbers and see what happens there. So I'm going to start by just writing down the original ordered pairs on the function. The original ordered pairs were -2, 1, 4, 1, and 6, 8. Now if I was to go through one by one, maybe I'll start with the shift right one. The shift right one means we're going to take the ordered pairs and not change the y value, so all of the y values will stay the same. A shift right of 1 means we're going to add 1 to each of the x values. So -1, 5, and 7. That takes care of my horizontal transformation. Then I go and I do my vertical stretch. Now we're not going to change the x values, but we will change the y values. So to change the y value, I'm going to double the y value. 1 times 2 is 2, 1 times 2 is 2, and 8 times 2 is 16. So this is just the vertical stretch part. Then the last thing we're going to do, again not changing the x values because we already did all of those, is we're going to subtract 3 from the y values for the shift down. And then these are my ordered pairs on my final transformed graph, which you should see match exactly the ordered pairs that we had when we did this graphically. We'll apply the same process here. Again, we're starting with the ordered pairs -2, 1, 4, 1, 6, 8. We still need to understand what the transformations are, so we'll start with the horizontal compression by a half, which means we're going to multiply each x value by half. Remember, do the opposite when it's on the inside. So we get -1, we're not changing the y values here. Okay. And then we do what's on the outside, which is to multiply the y values by -1. Now we're keeping the x value the same, but changing the y. So let's check. -1, -1, 2, -1, 3, -8. That all checks out. We have two more examples. F of -x. A -x on the inside of the function changes the function horizontally, and this should be a horizontal reflection. Now really, if you followed our rules, you would say divide by -1, but we know that dividing by -1 is the same thing as multiplying by -1. So we're going to reflect everything over the y-axis. A horizontal reflection is actually over the y-axis. So we take our ordered pairs. Let's do the numeric way first. We had -2, 1, 4, 1, 6, 8, and we are going to just divide the x values by -1, which is the same thing as multiplying by -1. And there's no y changes, so the y's should still stay where they are. So 2 times -1 is, -2 times -1 is 2. And we get -4, -6. So I'm going to plot the ordered pair 2, 1, -4, 1, -6, 8. So there is my reflection of my original function over the y-axis, or my horizontal reflection. So that's my new graph. Okay, now we have a more complicated inside change, f of 2/3 x. So I need to think, okay, it's telling me multiply by 2/3, but I really know that I am going to multiply the x values by 3/2, or 1.5. So that's actually going to be a horizontal stretch. Take our ordered pairs, and we're going to stretch them. So 6, 8, I need to multiply the x value by 1.5. So the ordered pair 6, 8 ends up becoming 9, 8, because 1.5 times 6 is 9. So here we are at 9, 8. 4, 1 becomes 6, 1. And -2, 1 becomes -3, 1. So I'm just multiplying the x values by 1.5. Now, the important thing to understand is that compressions and reflections always happen relative to the axis. So whatever the distance was from the y-axis before, I now have 1.5 times that much. Let's check by plugging in an ordered pair. So I'm going to check 6, 1. And I do that by plugging 6 into L of x. So L of 6 would be f of 2/3 times 6. Well, 2/3 times 6 is the same thing as saying 12/3, or 4. F of 4 is from the original function. F of 4 is 1. So I'm getting the ordered pair 6, 1, which does check. So I hope this video gives you some additional practice on function transformations and helps you remember that vertical transformations do exactly what they say they do, and horizontal transformations do the exact opposite of what they say they do.